Okay, hi everybody, good morning and welcome to ECS second Additive Manufacturing live webinar, Choosing the Right Technology and Software. I'm Terry, Division Manager of ECS, and I will be assisting to co-host in today's webinar. So just a few housekeeping notes to take note. At the bottom of the screen, you will actually see the Q&A tab. Okay, sorry, just let me start my video. Okay, so at the bottom of the screen, you will see the Q&A tab. So please utilize the section to ask any questions if you have. We will be answering the questions at the end of the webinar, and we will try to answer as many as we can. Any questions we are not able to get to, we will send a specialist who will reach out to you directly. And in today's webinar, we will be focusing mainly in 4 key points. What's material jetting and why do we need it? Indirect productions with commodity grade materials, and of course we'll be showing some case studies, and lastly will be why additive manufacturing software matters. We will then close the webinar with the Q&A section and survey. So before we move on, please allow me to take this opportunity just to do a very quick poll so that we can actually understand you better. So okay, just let me cut this up, and there we go. So as you scroll down, you will actually find 3 questions. Select the option that best fit you. It should take you about 20 seconds to complete, and once you have done so, click on submit, and that's all. Okay, you can see some of you have completed and submitted, and we will give everyone a few more seconds to do so. Okay. All right, we are done, and here are the results. Okay, we can see that most of the audience are from the academic and research industry, some from the consumer and the aerospace defense. Okay, which additive manufacturing technology are you more familiar with? Majority will be on FDM, followed by SLS. And which of these best describe a level of interest? Browsing, evaluating. Okay. All right. So to begin off, let me just do a brief introduction on the company, on our company profile. Omar, if you may. All right, so ECS has actually started since 1982, and we have been providing a comprehensive range of world-class CAD/CAM CAE solutions to the manufacturing, aerospace, marine, and offshore industries, mold makers, and many others. So we started 3D printing business way back in 2008. And of course, in 2017, we did a drastic change. We restructured the whole business offering, focusing just mainly on 3D printing. So having been in the 3D printing industry for 12 years, we actually expanded our presence across ASEAN, and we started our office operation in Thailand and Indonesia as well. So without further ado, let me introduce you to our presenters. And today, instead of one, we are bringing you 2 presenters. They are Omar and Jolene, and they'll be covering each on different topics. Both of them are our application engineers, and they specialize in assisting customers across all the regions to integrate additive manufacturing into their current workflow. And now I shall pass it over to our first presenter. Omar, over to you.
All right, okay. Good. Thank you, Terry. So, okay, As we have also discussed in the previous time, the intent that we have in running those webinars is more of like knowledge sharing. So perhaps I will do a very quick recap to also what we discussed in the first webinar when we went in depth into how the technology came about, how it emerged in the prototyping space, how designers used to be able to develop their prototypes previously using just subtractive methods. Those techniques were slow, and then a guy named Chuck Hull in the mid-1980s developed the very first 3D printer, which is known as SLA that we know nowadays, that uses liquid resin and laser light to be able to cure the part into plastic. We also saw generally how the industry is developing massively. So in terms of revenue, how the revenue is increasing from, let's say, or projected to increase from $10 billion to $35 billion in a matter of 6 years. We also discussed why we have such terms of rapid prototyping and how now it's better for us to call this 3D printing technology more as an additive manufacturing technology because of its uses in manufacturing, such as places in aerospace or automobile, medical industry as well. And the reason why people started to consider 3D printing as a manufacturing technology and use it for those end-use applications nowadays, rather than just sticking to prototyping, is the fact that additive manufacturing brings about design freedom. And we spoke about the differences between the restrictions that are there with design for manufacturing and assembly, which is the way we design for traditional manufacturing processes, and then how design for additive manufacturing allows you to create those complex shapes and without needing any tooling. So for plastic parts, that was the part that we went a little bit in depth when we saw the latest trends when it comes to resin printing or photopolymerization. We spoke about the non-contact membrane technology and how it allows you to go now and print hundreds of parts in a matter of hours and be able to give you resins or materials that can hold their mechanical properties. And that always used to be the challenge way back then when we couldn't get those parts to go into functional end-use applications. So we can produce all sorts of different textures and lattices and plastics that can take, let's say, 300 degrees C or go into medical applications. So overall, that was the trend. And then I had this slide that I stumbled across, and that one showed the 7 main technologies that we have in 3D printing, that each one of them in a way complement 3D printing. They have their advantages and disadvantages, and they're used for some applications to enable additive manufacturing to go and break into different industries. So today, we will just going to be focusing on one, and this is material jetting. Material jetting is a technology which is very interesting, very famous as well, applied heavily in different industries, and it really complements the trend of going into production with additive manufacturing, and we will see later why it does. So first of all, just to give you a quick introduction of how the technology works, material jetting is probably the easiest one to understand. So it works in a, in a manner which is very similar to what we get on a normal 2D printer or your photocopy machine. So we have a print head, and this print head, as you see here in the video, is traveling backwards and forwards. And this one, instead of just like jetting using the nozzle's ink, we're jetting resin and is getting cured with UV lamp right on the spot at room temperature. Also, it's also worthy of noting that we're jetting both the part material and the support material at the same time, using different nozzles, of course. So when it comes to speed, this technology is relatively slower to the other, let's say, non-contact membrane technology due to the fact that you still have to make the print head travel backwards and forwards, as well as that it also goes into Z direction to be able to create the part in 3D. And but the key thing that really makes this technology shine and stand out compared to all the other technologies that we have, the ones that we talked about, is actually the accuracy by which we can build the parts. So the fact that you're using those very precise droplets that are being jetted from the nozzles allow you to create and attain the fidelity and the accuracy, which is, let's say, equivalent to 10 microns or so in 1 inch of one part. So one thing we also have to mention here, and this is true for all 3D printing technologies, and we didn't touch on that last time, is that all 3D printing technologies, such as when you think of a building, for instance, you have to create a support structure while building the part in 3D. So they ensure that the part is being secured inside of the print bed. They also ensure that when you have like different features, they all attach to the same body. And most importantly, they allow you or ensure that the deformation is kept to a minimal state. So perhaps, and it's good that I saw in the poll that many of you also been using FDM, which is widely accessible nowadays, and I believe many of you are well aware of how we build support structure, those solid supports that you have to use. So for all printing technologies, whether we're talking about metal or FDM or resin, you were to have those solid supports that looks something like this in the picture, except maybe for material jetting and SLS. So in material jetting, we use a wax or a gel support, and we'll come later to that. And in SLS, we use powder support. So support is very, very important and crucial for the success of your part. So many of you are aware that in 3D printing, unfortunately, we have this phenomenon which is known as warp or sag, whereby you get a deformation in your part. And the reason why we have it in SLS, we have it in FDM, is due to the fact that we're applying heat. But the tricky thing here is it's not just heat, the problem that's causing this deformation, but the fact that we are applying heat in non-linear state. So when you're talking about a part which is being built, let's say we're going to take FDM as an example here, the part is being built layer by layer, and this is true for any manufacturing process. So the fact that the cooling of those layers would happen at different rates, you will more likely to have this deformation. In SLA or DLP, non-contact membrane technology, when you're using an open tank resin, you get a phenomenon which is also quite similar in a way, a deformation to your part, and this is known as sagging. So again, you have to make sure that the part is fully supported in all the features and the supports are being built correctly, so you were to get the geometry correct. But the good thing about material jetting that also corresponds to the accuracy is the fact that when you want to get rid of the supports, you will just either dissolve it in water or you will use an oven at, let's say, 50 degrees C or 60 degrees C, which is a lot less than the melting point of that plastic, to get rid of those supports. And the fact that you're applying the heat linearly across the part doesn't give you the different cooling rates across the part, and therefore you don't have any deformation. Or of course there could be, but it's definitely a lot less compared to the other technologies. So the same trend as what we also saw last time with resin printing, the material library for all 3D printing technologies is expanding. So now you can go around, you can produce transparent plastic parts that mimics glass. You can also produce biocompatible parts. You can produce tough plastics that goes into high heat applications, and we will see why those are quite important for some of the applications that we're going to show later on. And you can also, one of the good things that you can produce only with material jetting is the ability to produce natural wax. So one of the good things that we try to always utilize while building in material jetting is to apply lattices for your structure. So last time we spoke about generative design generally, and lattices can be parked in a way under this generative design. So instead of you building a solid part internally, which is the case for any traditional manufacturing process, you can now go around and produce a structure from the inside that has those interlinks, and therefore you're ensuring that the part would be maybe up to 70% lighter, depend of course on the part that you design, and correspondingly you will have a reduction in cost as well. So we also spoke about this last time. Good thing about 3D printing and why people are also using it, the fact that you can now get assemblies all together printed at the same time. So same for moving assemblies. This whole assemblies have been printed out from the printer, wax dissolved in an oven, and there you have it, all the moving assemblies. So in prototyping, this is quite important for companies to be more productive and to save times that were used to be spent to go around and assemble parts. Hinges, snap fits, again, the accuracy of material jetting is what makes it better suited for those kinds of prototypes. And perhaps what makes also material jetting really stands out, it's the only technology out there that allows you to print in multi-material. The fact that you're using a print head that has different nozzles, so you can jet different compounds or different materials at the same time. So if let's say you want to work on a prototype that has like rigid features and other elastomer kind of features or flexible features, you can print it all at the same time, all assembled together. And one of the very good uses for those multi-material printing would definitely be in the biomedical industry, whereby people, and especially doctors, if they want to practice for surgery, back then they would have to go around and get like real organs. But now the fact that you can design an organ in 3D and give it all the different textures and the rigidity and opaqueness and all the kind of features that would make it look like the actual organ, you can print it with material jetting and use it for practicing. This is, of course, cheaper and faster for them. So overall, and we have also many clients here that are using, most of the Fortune 500 companies, the big companies in engineering products, are using material jetting for their prototyping. The fact that it gives them the accuracy, the multi-material, and it also gives them the ability to apply color. So most of the engineering products that you see around you, whether they're the newer ones like iPhones or the newer tablets or laptops, I can assure you that most likely material jetting was the technology used in the prototyping stage. But overall, we saw last time that 3D printing, even though it really complements the prototyping stage, we're now trying to move into manufacturing rather than just sticking to prototyping. And we saw how in more advanced industries such as aerospace and medical, they're starting to use it more heavily. We saw how GE and Boeing are now 3D printing like 300 parts inside of one of their latest engines. So in what way does also material jetting help into this trend? And because at the end of the day, when we talk about 3D printing for additive manufacturing and for 3D printing for going into production, we still see those things that are attractive and lucrative for people to go into. The design freedom that comes about, the accelerated development time. We saw from previous time the development timeline for, let's say, injection molding, and how you have to have all those different steps that would take you weeks or even months. It's also, you're very much depending on producing with tools and molds, and in 3D printing you can do a shortcut and allow you to go around and produce toolless production and producing, most importantly, on demand. So people, supply chains and companies would have to be complex for a traditional manufacturing process, and the fact that you have to produce in hundreds of thousands, if not millions of items for you to be able to go into markets and produce. But now 3D printing, you can have a digital file and just print it on demand. And that, of course, give you a lot of cost savings. So this trend is actually what everyone nowadays is aspiring to, but there still remains to be some hurdles and challenges for us to reach this mature state of additive manufacturing and scaling it into production. So one of the very famous challenges that we also come by quite often is the workforce skills. This is a concern for many employers. Another problem is the integration into existing workflows, and materials, of course, remains to be also one of the hurdles. I will touch very quickly on some of those points in this webinar, and that will help you also understand what I mean about those challenges. So when it comes to workforce skills, one of the things that also makes people quite wary, the fact that this technology is quite new, how the software is quite different from the 3D modeling software. Employers are not very sure whether the staff is able to carry out the preparation for files and all sorts of applying like lattices and so on. And perhaps the development that has been taking place on software side has also enabled people to easily integrate and be able to use this technology. And in the second part, which will be handed over by Jolene, she will showcase how the software have become also more intuitive, and this step has become less of a hurdle these days. Second thing is integration into existing workflows. So this step would, of course, include many other challenges, but perhaps one of which that are very important for us to address today is the fact that for any part that goes into manufacturing, there has to be an industry-wide standards that are being applied. So I believe many of you are aware of the ISO standards, the ASTM standards for materials, for instance. And the fact that for traditional manufacturing processes, we have a complete and a very thorough list of those standards being written already for tens of years makes it easier. But this is not the case for 3D printing, which is relatively newer. So for you to get the quality assurance, you will have to draft newer guidelines for it. We see those companies like ISO and ASTM developing newer standards to apply for 3D printing, but the problem still remains that it takes months or even years for you to get your parts accredited. And when it comes to materials, even though we can now print ceramics and polymers and different kinds of metals, still I would consider that the 3D printing materials, because the technology is quite new and because the patents for this technology only expired in 2010 or something, so companies have only been able to develop materials from that time. So compare that to, let's say, casting or injection molding or some of the processes that we've been doing for more than 100 years, you were definitely going to get more materials on those compared to 3D printing. It's true that on daily basis, for those who are also keen and would look out for all the newer trends in 3D printing, you always come by new headlines for companies and research institutions coming up with newer plastics and alloys for you to print. But the fact still remains that when we go into production, we always rely on those commodity grade materials. So for plastics, polypropylene, Teflon, POM, those are used if, let's say, you're talking about food containers or water bottles. Those are chemically inert, non-toxic. We can easily process them in injection molding, and we have a full suite of their properties by using traditional manufacturing processes. We see that in 3D printing, we can start now to print some of them, but again, the shrinkage rates, the full suite of properties remains to be a challenge for us to get to. In metal, and I believe many of you are aware that in aluminium, for instance, or steel or titanium, you get different grades of alloys. Aluminium is not just one single alloy. So for instance, if we were to take like the 7000 series, you can see here the tensile strength and the ultimate strength is maybe almost double that of the 2000 series or the 6000 series. So aluminium can be used in very advanced applications such as aerospace and can also go into sliding doors or windows. So different grades would have different corrosion resistance and different machinability. And as of now, even though we can, of course, print directly in metal some of those aluminium parts, we still don't have full access to the wide range of those alloys. So we often hear from our customers, that, especially when we're working on proposals with them, that they really see the value of going and around and producing with 3D printing. They also want to go into tools production. They want to accelerate their product timeline, but they're not willing to give any concessions when it comes to the materials as well as the regulations part. So this is where we see material jetting really helping them, because we try to provide them with a shortcut, and this is known as indirect production. And just for me to highlight, different technologies can also provide you with an indirect production, but the fact that material jetting really gives you the highest accuracy, it makes it the best suited technology for us to use in producing molds and tools and dies that we saw from last time that in traditional manufacturing, you will have to use them to be able to create the geometry. So I will now showcase some of those examples from plastic parts to metal parts that will give you better understanding. I will also give some examples from the real customers that we have. So just give me 1 second and I will get right to it. So for plastic parts, one of the most production methods that we use is, again, injection molding. And for anyone who is doing injection molding, there's always a persistent challenge before they go and scale into production. The fact that the customers need sample parts, and those parts would have to be processed by molds again. And they try to go around and save costs by machining cheap aluminum molds or low-grade steel molds. Again, it takes them months or weeks to develop. It's, again, expensive, and the lead times are quite a lot. And the end goal here is for them to really just produce maybe tens or maximum hundreds of parts to give out to their customers to verify the design. And once they make sure that the mold has been designed correctly and the design of the part is conforming to what they have in mind, then they scale and go into production. So 3D printing and material jetting really gives you a very nice shortcut when it comes to this step. The fact that you can now go around, as what you see here, the green inserts and the white inserts, those have been 3D printed in tough plastic resins using material jetting, and they can take the heat of injection molding and produce maybe up to 100 parts. Of course, it depends on the material that you inject. Gives a very good competitive advantage to people who are applying it. So if you were to go and look into it, you will find that normally you're reducing the tooling time from 28 days, for instance, in this one example by a company which is doing some electronic parts, and then you're reducing this to 3 days, and the total costing also reduced significantly here. So we have a customer here based in Singapore that is a contract manufacturer and is also looking to accelerate the fact that the sample production part in that step. Again, he's not willing to make any concession when it comes to the injection process. So we've worked alongside with him and we tried to introduce him to that solution of producing the molds. And what you see here, I'm unable, of course, to share some of the pictures of the parts because there's some NDA signed, but the injection parameters are pretty much the same as the ones that we apply for, let's say, aluminum molding. So in that case, we were able to produce about 50 parts in COP. So again, we managed to get the same kind of savings as what you saw. Thermoforming is, again, perhaps a process that is used heavily in plastics again. So in thermoforming is what you see here in the video. It's being used in packaging. It's also used to make some dial parts, let's say indicators and some small plastic parts, as well as aligners. This process relies on molten plastic, vacuum, and most importantly, you have to have those tooling or die to create the shape. So again, with using the tough plastics, we can now produce those dies in 3D printing with material jetting. One good example is that we have here, we worked with one customer, and again, we managed to produce 3 tools for him. Each one was less than $100, and each one managed to give him 400 parts for packaging. So again, you can see how fast those were produced and the fact that you no longer need to machine them. A similar trend would that be of sheet metal forming. So interesting that in sheet metal forming, just to give you a quick introduction, when you have a sheet metal and you need to form it as what you see here in a video on the right hand side to a desired shape. This step, we also can go around and produce some of those molds using the material jetting technology. So again, similar to what we get on thermal forming, the integration into existing workflows is the key. Those resins can really take the injection or the mold massive kind of forces of 15 tons. They're again very cheap. If you need to apply any threads, they can also be applied easily in the software. So overall, gives you a lot of productivity. And perhaps when it comes to an industry that's also benefited tremendously from this trend is material and metal processing and casting. So I will just now play a very quick video and I will take it up from there. I'll do an explanation. And this one will give you a better understanding of what I mean by investment casting. All right, okay. Just for me to quickly highlight what you saw in the video. So investment casting is a casting process similar to sand casting or aluminum die casting, but this one gives you the highest precision. So previously, you were to have to go around and produce a mold, and then you were to inject the wax inside of that mold. Then once you have the part, as what you saw in the video, you go around, you assemble it in a tree, you cover it with a casting powder known as slurry, and then you heat the mold. You make sure that you melt out this wax, and the void which is created and the mold that has been, in a way we say, cooked or baked, is what you pour the molten metal inside. So this technique is used when it comes to processing of metals in very fine and precise kind of processing. So it's used in aerospace, it's used in automobile, and now you no longer need to go around and produce molds. So again, saving weeks, and you just, as what you saw in the video, you can directly print the part in wax. So instead of you waiting for weeks or months, you can now produce it in a matter of 24 hours. So one of the very good case studies that we have here in Singapore is one customer that is producing aerospace parts. So they need to have the quick turnaround for design cycles. When it comes to aerospace, I believe many of you are aware, there is very high kind of regulations. It's going to take them years if they need to develop those parts in metal 3D printing. So what they try to go around and make sure they make no concession into the existing workflows and regulations by just adopting those casting patterns. And they're now trying to go into more into low volume production and retrofitting using our printers. So if we're also going to be talking about casting and indirect production, an industry which has been completely changed by this trend is of course that of the jewelry. So previously, a designer would have to go and sit down and use all sorts of different tools to create the shape in wax in a very precise manner. Newer software in jewelry design allow you to go and produce those designs in 3D CAD. And once you have the part in 3D CAD, then you print it directly in material jetting in wax, and you can now overcome the shortage of those skilled working people. It's more productive, and of course the throughput when it comes to the speed is a lot higher. So when you have the digital file already, you can scale into production. You no longer need to make it piece by piece in a way. So in Thailand, we've been working with all the big players in jewelry manufacturing, and we've also been trying to go and advise them on, because when it comes to jewelry and when it comes to casting generally, you're not just casting in gold, but also different grades of golds and silver. So there are different considerations that you have to apply, and we try to always work in this industry. So another good examples that we have, Mitsubishi in Thailand again is using investment casting for some of the turbochargers that are used in the ICE. Previously, they were just looking at a prototyping technology to be able to go and produce just a few prototypes, but our guys in Thailand have managed to go in and convince them to use the latest machine that I just show a video for and go into production and some retrofitting, medical industry and dental implants. When you're talking about partial dentures, crowns, implants, again, can be produced in material jetting and wax, and then we cast that later on in metal. And one of the last things that I will just highlight also today is that when we spoke about design freedom and design for additive manufacturing, even though we're still now producing tools or producing molds or patterns, you can still tap onto the flexibility of design for additive manufacturing when you're applying this hybrid or indirect production technique. A very good case study and good thing that the customer has allowed us to share it is a company in Vietnam, which is called Tosi. They have a lot of patents and they're doing robotics. And this is perhaps a very good demonstration to what we see in design freedom and the fact that you can now go around in 3D printing and produce joint assemblies all together that cannot be done in traditional manufacturing, and they can now directly cast it in metal. So another trend that you can also see is with vacuum flask casting. It's again a casting technique that is using the same patterns in wax of material jetting. You can go around, you can cast the parts in magnesium. Magnesium is a light alloy, even lighter than aluminum. It has some applications out there, and it's hard for you to process in metal printing. And the fact that you can now go around, you can also produce those very intricate lattices. This can be achieved by the hybrid production. So overall, if what you're looking at is a shortcut for your certifications, you don't want to spend weeks or months for you to get the certified part for 3D printing. If you really want to go and have an access to the full wide range of traditional manufacturing materials, such as, let's say, magnesium alloys or aluminum alloys of all different kinds of grades, or perhaps in injection molding, you want to have POM, PP. Again, this is a very good shortcut. Also, in a way, if you want to break away from some of the traditional design restrictions, we saw in Tosi example how they go around and they produce those assemblies. And of course, overall, the tremendous saving when it comes to costs and lead times. And perhaps one of the very good things that also indirect production gives you in a way, and this is again a challenge for some of the 3D printing technologies which we will address now in a way, is the fact that it gives you the quality assurance or the consistency of your printability. And when it comes to the consistency of printability, it's not just a matter of hardware as many people might consider. Software and choosing the right orientation and creating the right support plays a very important role into that. So 3D printing software, generally, people might think that 3D printing, of course, it's easier. Of course, it's like a smart building manufacturing method compared to traditional manufacturing processes. You leave the printer running and the printer would do all the geometry creation by itself. But again, it's not as simple as just pressing of a button. So the link between the data that you design in 3D CAD, modeling software, SolidWorks, Creo, Autodesk Inventor, and the physical part that you get from the printer is actually this 3D printing software that you use in between. And the success of your prints really very much depends on it. So in the next part, I will pass it on to Jolene, who has been in this industry for 8 years, and she's been doing a lot when it comes to the software. And she will share with you on what are the trends and how the software has become easier to use. Overall, we can see now more integration of those software to additive manufacturing, but perhaps I will leave Jolene to hand over this part. So thank you so much, guys.
Thanks, Omar. Hi, everybody. Jolene here. Yeah. So for the software, there are certain considerations like what Omar has introduced that will affect the success of your print. So some of the issues that we want to highlight in choosing the right software from 10 years ago where like 3D printing software could only bring in STL file, we have seen a great improvement where there's a lot of integration now, where we can bring in native CAD formats like your STEP and Parasolid file. But in the end, the 3D printer still reads in a STL file. So there's a conversion done in the software itself. And this conversion to STL file is done differently in different software. So we need to ensure that the STL file has no errors, no gaps, and it's a good file so we can get a good printout in the end. Second point we want to bring in, it's in terms of SLA and DLP printing, we have a support creation that is required to avoid any warping or any effect on the part itself. So that area of support creation, how long it takes in the software and how easy is it to actually build your support is actually a great deal. Which brings me to my last point, which is file preparation. So the ease of the use of the software actually allows you to save on man-hour labor costs. And that is a great deal in terms of how 3D printing is moving into production. So the last point, 3D printing software now can even do certain optimization of parts or modify certain parts for additive manufacturing purposes. So like lattices or even splitting large parts into multiple small pieces so you can do printing in the restricted build volume. So following forward, I will just do a short demo on a software that we are currently using. It's called 3D Sprint. I will cover two examples in the software. One, it's in the support creation, and one, it's in the material jetting example. Okay, so this is the software 3D Sprint. It is a complementary software from any of the 3D Systems printer. If you bring in a file with error, you'll see that on the right side is red, and you can do the auto fix function where it will highlight all the errors like bad edges, open boundary, or any flip surfaces even. And the auto fix will be done in matters of seconds, and your file, once it's completely fixed, you can see that there's a green tick on the right side. So that's when we are ready to send it for build. So this one, it's in the SLA or DLP where support creation is required. This part here, there's a smart support function which will allow us to quickly auto-generate support. So in real time, we can see that the support generation is done in a matter of minutes, and we don't need to sit in front of the computer for hours in order to create support. And in any case where we consider the functionality of this part, where we have thread in between, we would not want any support to be there to compromise any of the accuracy of the build. So we could easily modify the auto support that is created. So going into the modify function, we could use the box function to actually erase all the areas, dots here that support is created. So in one go, the support is removed. And on further scrutiny of this part, I noticed that the screw also has support on the thread itself. So I can go back to the modify function, manually point by point remove the two dots there, and quickly update the support. So there we are. Once the support is done, my file is ready for printing. That's how fast the file preparation is. So this one, it's in the material jetting example. As 3D printing is moving into production, we can do multiple pieces in taking advantage of the big build platform in material jetting. So in the copy function, I can quickly copy the pieces to fill up the entire platform. So you see there are some excess on the outside that can't be arranged. Let me just do an autoplace to fit as many pieces as possible here. Yep, there are some excess pieces. So I will just remove those on the outside of the build. And what I'm going to do here, because of the support which is made of wax that Omar highlighted just now, in material jetting, we do not need to create support. It is all in wax and we can easily melt it off later in the post-processing step. I will actually be doing stacking of the parts. So we can take advantage of this function to actually do long hours overnight printing. And in the next day when we come in, we will have multiple parts ready for production. So let me just combine this entire layer into one group. So you see on the right side, you see that it's a group instead of multiple parts. And then I could easily copy this using the linear pattern copy in the Z axis. And I set a gap of an estimate of about 3 mm. And in closer look, I noticed that the gap is pretty close. And just to play safe, I will just increase the gap there so that the parts are not printed stuck together. Yep, now the gap is great. So we are ready to do even more stacking because you can see that the entire build volume of this material jetting machine is actually quite big. So let me do another 4 stacks there. Okay, let me just go back to the copy function. Again, using the linear pattern copy, I will do another 4 stacks. I can adjust the distance here accordingly so that I do not need to do any adjustments later. And you will see that the copying is done very quickly in real time. The video, it's in a matter of seconds, all the sets are copied and you do not have to do any manual arrangement. All sets are copied in just stacked above each other within the build platform. So once we are done, the part is ready for printing. I can just simply click add to queue. And this entire build will be sent to the printer. It also checks on the build volume and allows you to name what is the job name that you want to give. Like for example, this one is a test marker. So in the queue format, you actually see your job appear. Now I'm not connected, so you can't see it actually. So in the queue, let me just touch a bit on the queue. So in the queue, what we can do, we can actually rearrange the files that we have sent to print. So how do we actually optimize the printer for use? If this print is a long hour printing, I would want to do it like, let's say overnight. And if it's a short hour printing, I could easily do it during working hours. So let me just use the estimate function. And then I get the estimated time for this entire stack, which is about 10 plus hours. So in total, I have about 200 odd pieces here. In 10 plus hours, it can be produced in the accuracy of material jetting, which is very, very reasonable. And the materials used are also estimated. So in the newest format of this, newest update of this software, it even allows for this sparse support creation for casting purposes, where it's very easy to remove by hand. You can see here in the video. And this is because we want to reduce the amount of post-processing time needed on the casting part before it's actually casted. So to produce a best casted part in the end. Okay, so let me just highlight some of the benefits that we have walked through. Over the entire software, the 3D Sprint software, you can see from the short demo, it's very intuitive. You don't need like hours or days to even learn how to use the software. It's very easy to use. From the past where we had to spend hours of preparation before we can actually send a build to the printer, to now, it can be done in less than an hour. And smart support building, you can see that the support is very easily created in a matter of minutes, and any modification in terms of functionality can be done easily. And finally, it gives me back to productivity. The ease of use of the software actually allows for man-hour reduction costing, and arranging of the queue actually allows you to print and use the printer in terms of overnight printing, and scheduling when do you want to do the print. Okay, let me pass it back to Omar.
All right, okay. Thank you, Jolene. Thank you so much for the demo. I believe the entire thing was maybe about like 8 minutes or so. And really that was the same speed that we try to use while making our parts. So again, we saw how it became more easier. It's a good thing that the trend now in the industry, people are paying attention more into designing easier software that can be easily integrated and allows you for more productivity. So I will just now conclude today's webinar and also share about what we have upcoming, about the upcoming one. We spoke a little bit today about, support structure. You can see from the trend that we're starting to go more in depth of how you can make sure you get the part right. And perhaps we cannot talk about production for 3D printing and not mention metal printing and powder bed system. So in metal printing, it's a little bit more trickier. The fact that the orientation really also gives you different microstructure, and there has to be different considerations. So stay tuned for our upcoming one in July, where we'll go more in depth about this technology, the strengths of direct metal printing. We saw today that the indirect production is actually a good way by which you can overcome and process some of those metals. But again, you would still need to have an investment casting foundry and a whole setup in place and all the certifications and workforce that can be applied. But metal printing also brings about a lot of functionality, brings about a lot of productivity when it comes to the fact that you can have a closed chamber, a printer that can give you metal parts. And we will also see some of the simulations, some of the generative designs. We will, today we featured Jolene and showed you some of the software. We will also bring more experience to the table. So thank you so much for joining us today. And I will perhaps just hand it back to Terry and go into the Q&A section. Thank you, guys.
Okay, thank you, Omar and Jolene. The presentation is amazing. Thank you so much. So, all right, I'm actually quite thrilled to see actually there's quite a lot of questions coming in. Even from the beginning of the webinar. So, okay, Jolene, Omar is back. All right.
Okay.
So I'm just going to go straight to the Q&A session so they can try to address as many questions as possible. Okay, there's one question. In one of the video, it shows the support material melt off. Is that wax? Can it be recycled? If not, how to dispose it?
Okay, I guess I will answer this one. So yes, that's a wax material, which is quite similar to candle wax that we use. It's being jetted out of those nozzles. And can it be recycled? I believe so, because it's natural wax. It doesn't have any resin or artificial kind of compounds, and it's also safe. So it gets completely melt off, and the rest of the wax that it gets deposited, our customers would normally just discard it normally as any kind of waste. So yeah, I believe.
Okay, and we have a question on software. Can you just name the software you just showed, and does it has the intuitive to optimize printing position?
Okay, so the software, it's a 3D Sprint. It comes complementary with all 3D Systems printer. And that's really a great point that like you don't have to pay for it. And the software allows for, in terms of support creation, it allows for optimizing in terms of print time and in terms of the reduced support use. However, you have to take into consideration your functionality of the parts, like for example, the screw case study, the screw thread case study that I shown. So in terms of functionality, you have to just relook at the support and modify it from there.
Okay, I hope that answered. All right, next question. Okay, this is directed to Omar. Okay, in examples of using print for injection molding,
Yeah.
in particular, how many shots can you actually achieve from a printed insert?
Okay, printed inserts. It really, there's some considerations that we have to take note of. So first of all, depending on the material that you inject. So in plastic, thermoplastics, they also have different range of hardness and strength. So polypropylene, polystyrene would be on a lower end. Perhaps you can get some of those like ABS, slightly tougher, and glass filled. So if you're talking about those materials that are softer or would have what we call lower flowability, you can get maybe up to 100 parts or even slightly more than 100. But when it comes to glass-filled plastic parts that are tougher, perhaps you can only get 10 parts. So again, and the fact that you also, the injection parameters that you apply, the cooling time, all of those in a way give you the degradation for your mold as well. So if you apply it right, if you give it lesser force, you allow it to cool, and you give it more time for it to cool down, then you were to have more chances of keeping this part with no degradation, the insert, for slightly longer time, and therefore you will have more shots.
Okay, great. All right. And for material jetting, you keep mentioning about accuracy. So there's someone asking you, so what kind of accuracy can they actually be achieved?
Okay, so accuracy, it's about, okay, there's one linear equation that we have for our material jetting technology. It's about, if I'm not mistaken, it's about 20 microns per inch of one part. So if let's say you're talking about a part which is 1 inch, 25.4 mm, then you will have an accuracy of about maybe 20 microns or so. The more you increase the length, then the accuracy would also be, like correspondingly would have to be adjusted. So if you're talking about 50 mm, then it's about maybe 40 microns, which is 0.04 or 0.05 mm. Again, this kind of accuracy, even though it's worthy of highlighting that other SLA technologies that uses fine laser, the laser is very fine, but the fact that you're still building in an open tank and you're still relying on those supports is what we see, unfortunately, would give less or like more deformation to your part, especially if the part has like thick cross sections or like features that are longer and are not very well supported. But material jetting, in a way, because it's more like plug and play and the support structure really makes sure that the part is fully supported, gives you better accuracy in that regard as well. So yeah.
Okay. All right. And there's the question in the early beginning of the presentation. There's actually in one of the slides that shows a block with lattice inbuilt.
Yes.
So in cases like that, how do you remove the support material within an enclosed block?
Okay, so that is again a feature in the software. I believe this is available in 3D Sprint and probably available in most of the newer 3D printing software as well as that. You have a lattice feature that you can easily apply by just specifying the geometry and all the different latticing kind of interlinks that you're going to design. This is easily applied. I believe Jolene can also highlight on this. And there is another function known as holes. So perhaps Jolene can talk about this.
Yeah, so there's a function, so the lattice are applied on the inner area of the block, and to remove the support, as highlighted earlier, the supports are all wax, so we could actually build a hole for the wax to be drained out, and we could even build a hole for air pressure so that the wax is drained out even easier.
Yes. Yeah. So it's very easy for you to do, especially material jetting.
Okay, all right. I think we only got time for one last question here. So, okay, what's the difference in terms of the wax used for casting, and you also mentioned about support material. So what are the difference of those wax?
Oh, so like for instance, when we go in casting, if you see in the video, you saw this green wax patterns and some are like purple. The wax is different. The support wax is still a wax material, but when you go into casting applications, the wax is slightly harder. It has a higher melting point, so you make sure that you dissolve this support wax without dissolving the main build part wax material as well. And it's harder. It's the melting is also quite different. And I believe that depending on the part that you cast, you would have to do different considerations. The surface finish is smoother. And this is very important, again, for investment casting, especially for jewelry, when you try to get this, what's it called, like smooth surface finish. So again, the compound is different. Those are different waxes. The support and the build wax are quite different in a way.
Yep, and in the last video, you see that there's like a sparse support wax creation. So support wax can be created in terms of like sparse support, and it can be like easily removed, and the wax that you actually cast is fully solid, so you can get the actual part itself.
Okay, all right. With that, we thank you for joining us today. We hope today's talk will be of value to you. If your questions has not been answered, do not worry about it. We will actually reach out to you directly shortly. And before we end, I will just quickly just kind of like I want to get some feedbacks from you guys. So if you can, there will be actually 5 questions. All right. So just help me to submit your feedbacks. Okay, I'll just give another minute. Okay, all right, and all right, we got the votes, and no, we got the feedbacks already, and all right, thank you so much, and yep, it's no doubt it's phase 2, but please stay safe, stay healthy. Thank you, everybody. Goodbye.